Hi, I'm Moritz from Heidelberg University, and I compared two different methods to map subgroups onto CPUs. Okay, let's start with some introduction. So, as probably all of you know, SYCL is an industry standard developed by the Kronos Group to enable heterogeneous device programming using modern C++. And so this does not only mean to execute your code on GPUs, but also, for example, on CPUs. And SYCL is a standard, so it has multiple implementations, and I implemented this work on a fork of AdaptedCPP, which is an open source implementation of SYCL. Then SYCL supports a hierarchical SPIMNI model called ND-range parallel 4 execution model. And in this model, you write a kernel, which is a scalar function that gets instantiated multiple times. And all these instantiations differ only in a single input parameter. These instantiations are called work items in SYCL. Then these work items are arranged together into subgroups, and the size of a subgroup is implementation defined. Then subgroups are part of a workgroup, and the size of a workgroup you can specify by a parameter. Then workgroups are part of an ND range, which is a 1 to 3-dimensional range of work items, and its size and dimension you can again specify. Okay, to solve problems that are not embarrassingly parallel, you need to use some means of synchronization. And SYCL provides us with workgroup and subgroup barriers. And the semantics of them as follows. If a work item reached a workgroup or subgroup barrier, then it must wait until all other work items in its workgroup or subgroup have reached the barrier. Okay, then now let's have a look at how AdaptedCPP currently maps kernels onto CPUs. Well, it uses a method called continuation-based synchronization, or in short, CBS, that implicitly synchronizes between the work items in the workgroup. And that's a method that was proposed in a paper by Heidelberg and SYCL. Okay, let's have a closer look at how this method works. So here we have a simple kernel without any barriers. And now the basic idea is how to map such a kernel onto a CPU is just to put a loop around it. So the whole region is very free, so we can just put a loop around it. And this loop then iterates over all the work items inside the workgroup. And we call such a loop a work item loop, and I will call it from now on. Okay, but what if the kernel has a barrier? That's the interesting case. Well, now we have two barrier-free regions, the region in front of the barrier and the region after the barrier. And now we can split the kernel at the barrier and iterate over both these regions separately. So we just put work item loops around it. And now we implicitly fulfill the requirements of the workgroup barrier because no work item will execute the second barrier-free region before all work items have executed the first barrier-free region. Okay, but how does AdaptedCPP currently map subgroups onto CPUs? Well, to recap, the size of subgroups is implementation defined. And so AdaptedCPP chooses the subgroup size 1, which means that synchronization between the work items inside the subgroup is a norm because there's only one work item in the subgroup, and so no one to synchronize with. Okay, but this of course has its problems. So first, to make clear, if you have a kernel and this kernel uses subgroups, then it typically only supports one subgroup size. If you write your kernel for the subgroup size 32, then you can just execute it with the subgroup size 16 or 1 or whatever other subgroup size. And because 32 is the subgroup size of NVIDIA and many AMD GPUs, it's the most common subgroup size. Then the most important point is subgroups of size 1 are useless. So the advantage was that no synchronization is necessary, but it's also the disadvantage. There's no reason to use them. And the last point is that, well, you could write some algorithm that uses subgroups and is generic over different subgroup sizes, but it is more difficult to support the subgroup size of 1, because you could imagine some kernel that uses subgroups in a recursive fashion, and if you have a subgroup size of 1, then you can't make progress with it, and so this kernel would not terminate without some sequential step that combines all results at the end. Then are subgroups even an important feature? Are they used? Well, on NVIDIA GPUs, or generally on modern GPUs, you have hardware level support for them. For example, on modern NVIDIA GPUs, a work item can directly access the registers of other work item if they are in the same subgroup. So you have really fast synchronization. So, and this basically means if you have some problem and you can use, and this problem is not embarrassingly parallel, so you need some synchronization and you can use subgroups, then you should use subgroups to achieve the best performance possible. And so there are quite a lot of kernels that use subgroups. And so we want to have an efficient subgroup implementation that supports subgroups in a reasonable manner, so subgroups with sizes greater than 1, for example. So the first method we call hierarchical CBS, and as the name already mentions, we just apply hierarchical CBS hierarchically. So we first apply it on the workgroup level to handle the workgroup barriers, and then on each workgroup barrier free region, we apply it again to handle the subgroup synchronization. Okay, let's have a look at an example. So here we have a kernel with a workgroup and subgroup barrier. So first we apply CBS on the workgroup level. So we have now 2 workgroup barrier free regions. Now we split the kernel at the workgroup barrier and put the work item loops around the workgroup barrier free regions. Now, one small difference is that we don't directly iterate over the work items inside the workgroup, but over the subgroups inside the workgroup. And now on these 2 workgroup barrier free regions, we apply CBS again. So we have now these barrier free regions, and now we just put work item loops around them. And now the innermost work item loop iterates over the work items inside the subgroup. Then the other approach we call a whole function vectorization approach. And here we first remove all the subgroup barriers Then we apply continuation-based synchronization to handle the workgroup barriers. And then we vectorize the work item loop using whole function vectorization. Okay, what is whole function vectorization and why do we vectorize loops with it? Well, it's a generalization of outer loop vectorization proposed in another paper by Heidelberg and SYCL. And it gives us the guarantee that every instruction in a function, or in a loop for that matter, is executed for every vector lane in lockstep. And there exists the region vectorizer, which implements whole function vectorization, and we use it. Okay, now why does this work? So we first choose our subgroup size, for example, 32, and then we fix the vector with that the region vectorizer uses for the work item loop with 32. So in each work group where we have a region, the subgroups have the same size, and one work item always is uniquely assigned to one subgroup. So, and now this means that we implicitly map subgroups to vectors and the work items inside a subgroup to the vector lanes of the vector. And now, because of the guarantee of whole function vectorization, this means that every instruction gets executed for every work item in a subgroup in lockstep, which in turn means that every work item in a subgroup executes all instructions in front of the subgroup barrier before any work item executes instructions after the subgroup barrier. And so we fulfill the requirements of the subgroup barriers. Okay, then SYCL also has so-called SYCL algorithms, which can be roughly split into categories, algorithms to exchange data between work items inside a subgroup or work group, and algorithms to cooperatively do some computations inside a subgroup or work group. And one example of such an algorithm is a reduction. So reduction combines all the combines for each gets from each work item one input element and uses a binary operation to combine these elements into one result. For example, if you use addition as the binary operation, then the result would be the sum of all the input elements. And these algorithms are implementation provided, so we can use a lot of tricks to make them really fast without decreasing the performance portability of SYCL kernels. So for whole function vectorization, we use RV intrinsics to access the underlying vector abstraction directly. So we have our reduction function, then we can directly access the input vector. And now the idea is to implement the reduction, that we just split the vector in half, and then we can add the right half to the left half, and then we do that recursively until we get our result. For hierarchical CBS, we do the computation on one work item, so sequentially. This leads to good performance if LLVM is able to recognize that only in one iteration of the work item loops there happens actual work and removes the other iterations. And this is also the same pattern that's currently used to implement workgroup algorithms in adaptive CPP or the CBS implementation. Okay, we want these algorithms to be really fast, and one idea we had is that we can directly map these algorithms to vector instructions. So for function vectorization, we already do this, but RV does not or did not have a reduction intrinsic, and we added it to RV. And this reduction intrinsic directly maps to the LLVM IR vector reduce instruction. And we did something similar for hierarchical CBS so that we could directly map the subgroup reduction to the LLVM IR vector reduction instruction. So for whole function vectorization, this does not appear to make any difference, probably because we already use vector instructions and the hardware ISA does not support vector reductions, so there's no real reason why it should make a difference, so this is not unexpected. Then for hierarchical CBS, there's a huge difference. So we have a geomean speed up of around 1.75 compared to the manual sequential implementation I have shown on the last slide. Okay, then let's come to our other benchmarks. But first we use 3 different machines to run our benchmarks, 2 server CPUs that support AVX2 and 1 consumer CPU that supports the AVX 512 extension. Okay, our first goal was to find the best performing subgroup size. And here you see the geomean speed up over the subgroup size 32. And we use adaptive CPP's JIT compiler or compilation path. And for hierarchical CBS, 32 is the best performing subgroup size, with 16 being a close second. And for whole function vectorization, 16 is the best performing subgroup size, with 32 being really close to it. And these results are quite promising because 32 performs, the subgroup size 32 performs really good, and I don't think that there are many kernels that use subgroups but have no version that supports the subgroup size 32. Okay, then we compared whole function vectorization directly against hierarchical CBS, and whole function vectorization outperforms hierarchical CBS with a geomean speedup of 1.7. Again, from now on, we only use the subgroup size 32, and again, with adaptive CPP's JIT compilation path. But this does not mean that there are no benchmarks where hierarchical CBS performs well. So in the Eve minor benchmark, hierarchical CBS is twice as fast on the two server CPUs, and only on the Cent4 consumer CPU, whole function vectorization is a bit faster than in the Porter's JR benchmark. Hierarchical CBS is on all P machines faster, and in the Porter's EMX benchmark, again, only whole function vectorization is only on the Cent4 machine faster. Okay, but on which benchmarks does whole function vectorization perform really better than hierarchical CBS? And one example would be matrix multiplication. Here we observe speedups of up to a factor of 8. And the reason for that is the difference in the vectorization pattern between hierarchical CBS and whole function vectorization. So hierarchical CBS uses LLVM, and LLVM is best at vectorizing the innermost loop, while with whole function vectorization, we always vectorize the work item loop. And so in this case, vectorizing the outermost loop leads to contiguous memory access pattern, while vectorizing the innermost loop, if LLVM vectorizes this loop, then it needs a getter, so this is strided memory access pattern, and then at the end there's a vector reduction needed to combine the result. But this now does not mean that outer loop vectorization is strictly superior to inner loop vectorization. It depends on the loop list and the dependencies, the trip count, and so on. Okay, then we also compared these two approaches against the current upstream implementation that uses the subgroup size of run. And here we observed a geometer speed up of over the upstream implementation of around 2 for whole function vectorization, and for hierarchical CBS we observed a speed up of around 1.5. However, there's one interesting thing we noted. So this implementation pattern for the SYCL algorithms for CBS, so that you have a sequential implementation that's executed on one work item, and then the result is broadcasted to the other work items, does not work that well in all cases without or with the LLVM 16, and we also tested it with other LLVM versions. And we also try to make some try out to change the order of some of these passes. But in some cases, LLVM is not able to recognize that the computation only happens in one iteration of the loop, and to basically remove the loop and have only this one iteration. Okay, to conclude, both of these approaches to perform appear to perform quite well on our benchmarks, and in this case outperform the upstream implementation, and whole function vectorization is slightly faster than hierarchical CBS.
Time for a couple of questions. Again, front row first. I would like to ask, because I haven't able to understand from the slides, how it can be implemented for the generic case. Like, for example, we have a sales subgroup barriers, just group barriers. I mean, how it could be implemented, for example, in adaptive CVP. Are you plan to manipulate by abstract syntax tree in the compiler, or you somehow plan to insert these loops via some sort of preprocessor magic?
I don't think I understood the question. So you.
Well, I mean, just to reiterate, you have demonstrated how we can split one kernel with barriers into like several kernels in order to have a group barrier being emulated on the CPU, as well as insert some loops to ensure subgroup barriers, right? You could go to the slide.
Where we don't split one kernel into multiple kernels. So we split it at the barriers and then we wrap loop around these regions. So it's still one kernel.
No, okay, but how you insert these loops?
Insert. What do you mean with insert?
Well, how you add them in the executable code on the CPU?
How
they appear in the like final assembly?
We have a Clang plugin that transforms the code.
So you add this on the compiler level for
it's not library only. Yeah.
Okay, thank you.
I know, if I remember correctly, adaptive CPP have also an OpenMP backend. In OpenMP, do you use like just Pragma LCMD and you cross your fingers that the compiler vectorize? Oh, just curious, maybe sideway. It's like another approach is like relying on another programming model and not doing it yourself. I'm just curious if you know.
I don't have much experience with the OpenMP backend, but I think what you say is true.
Okay. Yeah, it would be interesting to see if your approach is more robust than the SCMD vectorization of OpenMP in some benchmark. I think it would be a nice comparison.
Wants to answer.
I can maybe add to that. So for our OpenMP backend, that's basically what we do. So that's like just a part of the OpenMP backend when we use a compiler. Right now in upstream, we only use this one level of continuation-based synchronization, so we don't split that to subgroups. But for each of these work item loops, we say, oh, by the way, this is basically an OpenMP SIMD loop, because we know that there's the semantics that all XSCs in here have to be well-defined in parallel, because that's what the SYCL SIMT model basically is, right? So that we basically do exactly the same as Pragma OpenMP SIMD would do, but it's, well, we still have to rely on the LLVM vectorizer, which doesn't really work well with the outer loops.
Thanks for the talk. I see in many of your benchmarks, there is difference between Broadwell and Zend on one hand and Zen 4 on the other. Like, not consistent, but basically often they are for like two different groups. Yeah.
You mean this?
Like here, yeah. Well, not the first one, but the left, the S minor and port bus LAMAX. Do you think it is related to the AVX 512 support in Zen 4? And if so, how do you think it will behave with even longer vectors? Like we have the 2 kilobit FPGA based architecture on one of the posters.
Well, Zen 4's AVX 512 support is where they do double pumping, so they have, I think, vectors that are 512-bit wide, but the LLU does the computation on 256 wide vectors. So, but I think it still has better vector performance than these two other architectures. And I think that it has a big cache, and it's also a consumer CPU with a high bandwidth that helps with it.
All right.
Yeah, and I think in the future that the performance of the subgroup size 32 with whole function vectorization will get better, because most of these benchmarks use 64-bit floating point numbers. So you have some implicit loop interleaving, which might help to hide memory access latencies. But if the hardware vector size gets bigger, you could maybe use bigger vector widths and this way achieve even better performance. But it's hard to predict the future.
Right, let's thank speaker again.